Section 9.3 is about testing um, if a series converges or diverges using the integral test. Now, what the integral test does is it looks for sort of an easy way to figure out if a series converges. That means if it, like we talked about last time, sums up to a real number, or when an infinite series diverges. That means the sum either does not exist or goes off to infinity. And again, in the next couple of sections, we're going to look and try to figure out some easy ways to determine whether or not a series converges or diverges. So this is our first approach. So this first approach makes a connection between the infinite series and integration of the function that gives us the infinite series. Excuse me. So let's assume that we have a function which is positive, continuous, and decreasing. And this function, when I input the positive integers, gives me the terms of a sequence. If that is the case, then this infinite sum from 1 to infinity of the sequence, so this infinite series, and integrating from 1 to infinity of the underlying function, both have to either diverge or both have to converge. So if the integral converges, so does the series. If the integral diverges, so does the series. Now, when I say converge, these will not necessarily converge to the same number. Okay, so if this integration comes out to 2, it is not the case that the infinite series will add up to 2. Okay, that this may integrate and give you a 14, and the actual series may add up to 3.8. Who knows? But the point is, they're either going to both converge or they're going to both diverge. Now, this is very specific. This f of x has to be positive so that we can connect this. We don't want to actually jump it back and forth between positive and negative numbers, things like that. So this only works when f of x is positive, continuous, and decreasing. Oops, I got a typo here. This is the graphical reason. So I'm going to try to give you the graphical reason why the integral test works. In other words, I'm just going to give you sort of a diagram of what's actually happening here. So I'm going to try to do this over the computer. It's not always the greatest thing to do, but that's what we got. Whoops. Let me go undo that and select, kind of move this down. Dang it. I apologize. Okay, so let's take a sequence which is positive and continuous, well, positive and decreasing. So let's go a little bit thicker here. When I input the number 1, I get out the number 4 into my function. Again, what we're assuming here is that, let me go to, what we're assuming here is that when you input positive integers in, we get the terms of the sequence. And again, if you think about n, an, we get a point on the graph like we've done before. So let's start when I plug in 1, the first term in my sequence is 4, then maybe the second term in my sequence, again, we just play around with this, maybe it's 2.5, and we start decreasing, And if it has to be positive and decreasing, then we're going to look something like that. We have to stay above the x-axis, obviously. All right. Now, if you think about what's going on there in terms of f of x, well, f of x is just going to be a continuous line. Let me try to draw this. Let's go a little bit thinner. It's going to be a continuous function, and it's going to hit and go through all of these points. I didn't draw this very well, but you can see what's going on. All right. So what this result says is that there's some connection between the sum of the sequence and the area under this function. Remember, that's what integration does. Integrating from 1 to infinity gives us the area under f of x. And so, in short, what that connection is, let's see if I can, yeah, I guess we'll use that again, is if you notice this height where my first term of the sequence is 4, this height is 4. If I translate that into an area, I can translate that into an area very easily by just taking a rectangle. I didn't draw that very well, but a rectangle here with height 4 and width 1. And then I can take another rectangle for my second term in the sequence. This one has height about 2.5 and width of 1. Notice that the area under this rectangle and the area under that rectangle are the first term and the second term in my sequence. So when you sum up all of these rectangles, what you're actually getting, so you sum up all of these rectangles, what you're actually getting is this infinite series here. Now you can see by the way I've drawn these rectangles that if the area under this curve is finite, in other words, if the area under f of x is a real number, then these rectangles have to add up to a real number because these rectangles, all except for this first one, are all underneath this curve. That's why we needed to have a decreasing sequence. We needed to have a positive sequence of numbers, or functions should have been positive so that we could actually do this, getting area underneath, and then decreasing because then that shows us these rectangles are always underneath the curve. Now, the other way, what if we had the area underneath this curve to be infinite? Well, simply put, we could have drawn our rectangles the other way. We could have said, well, this rectangle here, instead of drawing it to the left, let's draw it towards the right. Let's draw this one towards the right. Let's draw this one towards the right. Because my function is decreasing, if the area underneath this black curve is infinite, then obviously these red rectangles, which are the infinite sequence itself, are all bigger, and therefore the sum of the area of these red rectangles also has to be infinite. So because of the connection to area under the curve, we can see that if the area under this curve is finite, if it's a real number, then those black rectangles that I drew were going to be finite. And if the area under this curve is infinite, then these red rectangles I drew are also going to be infinite. And it works in reverse as well. I won't go through the reverse because the reverse isn't the real interesting part of this section. So there you go. The connection between infinite sums and integrals, either both are going to converge or both are going to diverge. So let's take an example. Let's take the infinite sum, again, n equals 1 to infinity, of n over n squared plus 4. So I'm going to do this on my own, or on a separate sheet of paper. To do that, we got to make a connection. So we take this infinite sum, n over n squared plus 4, and we say, well, n over n squared plus 4, that's just like this continuous function, x over x squared plus 4. So when I plug in positive integers, I get that thing. Now, this function is continuous, at least continuous over from 1 to infinity. Excuse me. So it's continuous. It's positive. There's no way I can get a negative number here. And it is decreasing. You can check that as you increase your x, this function does in fact go to 0. All right? So this is a function that is positive and decreasing. So what we can do is we can go back to our techniques that we learned in Chapter 8 and integrate x over x squared plus 4 from 1 to infinity. Now, if we're going to do that, the easy way to do this is through a u substitution. Take u equaling x squared plus 4, and then the derivative of u with respect to x is equal to 2x. So what we can do is we can replace 2x times dx with a du. Now we have an x times dx, we don't have 2, so what we can do is divide both sides by 2. We'd end up with 1/2 times du is equal to x times dx. So we can replace, let me highlight this x dx with a 1/2 du, and obviously x squared plus 4, we can replace that with this letter u here. Okay, and so when I go to integrate, we're going to be integrating. Now, by the way, it actually does not start at 1 anymore, because when x is 1, u is actually 5, so technically it starts at 5, but that's not the big deal. The big deal is that we get 1/2 over u du. All right, let's make everything dark. There we are. Hopefully you can freely change 1/2 to 0.5 or anything like that if you wanted to. So when you integrate that, what you get is you get 1/2 or 0.5 times the natural log of u. Obviously, we're going to evaluate that from lower bound to upper bound. I'm going to leave that off right now. Let me go ahead and do that. I'll leave the bound. I'll put the bounds on something like this. Now that you see that, I'm not really concerned that you put the bounds on at that stage because we're about ready to back substitute. We're going to get 0.5 times the natural log of x squared plus 4. And we're going to evaluate that from a lower bound of 1 to an upper bound of infinity. Okay, so from 1 to infinity, I'm using that because we're back utilizing the x's. And so what you do is you take the limit as x goes to infinity of 0.5 times the natural log of x squared plus 4 minus 0.5 times the natural log of x squared plus 4 when you plug in 1 for x. So again, what we're doing is we're essentially going to plug in infinity here, plug in 1 there, and then evaluate it. Now, I say plug in infinity, that's sort of bad language. Again, remember, we're taking the limit as x goes to infinity. But as you can see, infinity squared is going to be infinity, plus 4 is infinity. The natural log of infinity is infinity. So that first term gives us out infinity. The second term is going to give us out some real number, but take infinity minus real number, you just get infinity. So what does that mean? Whew, that was a long one. Well, that means that this integration here actually diverges. So this integration that we had diverges. Based on the integral test, that means that this series also diverges. So even though the series had individual terms which went down to 0, it didn't go down to 0 fast enough to converge. Therefore, this infinite series diverges. Hopefully that all makes sense. So here's what I'd like you to do. I would like you to use the integral test, integrate a function which is continuous and decreasing, continuous, positive, and decreasing, and determine whether this infinite series converges or diverges. So this infinite series is the infinite sum of 1 over n to the 1.5 power. Go ahead and push pause on the video, and then I'll explain that in about 4 or 5 seconds. So this infinite series, 1 over n to the 1.5 power, think function is 1 over x to the 1.5 power. We're going to integrate that function from 1 to infinity. If you do, sometimes it's easier to think of integrating from 1 to infinity of x to the negative 1.5. Add 1 to that exponent, you get negative 0.5 on that exponent, and then divide by the negative 0.5. When you divide 1 by negative 0.5, you end up with a negative 2. By the way, if you'd rather, you can, think about that as negative 2 over x to the 0.5 power, if that's easier for you. And then obviously we're going to plug in, I didn't write the bounds here, we're going to plug in a lower bound of 1 and an upper bound of infinity. So we're going to take the limit, actually, my apologies there, there's a better limit operator. The limit as x goes to infinity of negative 2 over x to the 0.5 power. All right, so that's our upper bound. And then we're going to also plug in 1. So when you plug in 1, you end up with, negative 2 divided by 1 to the 0.5 power. Okay, so upper bound and lower bound. Probably should have done that. Okay. By the way, when you take as x goes to infinity, this denominator is going to get bigger and bigger and bigger. The numerator is just going to stay at -2. Denominator, as it gets bigger and bigger and bigger, this whole fraction goes to 0. So you end up with that first term of 0, and then minus a minus 2 over 1 to the 0.5 power. 2 divided by 1 to the 0.5 power is just 2. So you end up with a plus 2. And therefore, this integration converges to 2. All right. Now, when we go up to my infinite series and say whether it converges or not, we know it converges. However, it might not converge to 2. It might converge to something very different. It might converge to 3. It might converge to, who knows. But it converges, just not to 2. All right? So there you go. Now we can determine whether this infinite series converges or diverges based on the integral test. Now let's do the next problem. I want you to go ahead and see what happens with this infinite series. Push pause on the video and use the integral test with the sum from 1 to infinity of 1 over n to the 0.75 power. Hopefully you did that. So here we go. Infinite series, sum of 1 over n to the 0.75. Our function here is 1 over x to the 0.75, and we're going to integrate that function from 1 to infinity. When you integrate that function, you can start, if you want to, by calling it x to the negative 0.75, add 1 to that exponent, you get 0.25, and then divide by that 0.25. 1 divided by 0.25 is simply 4. Obviously, we're going to plug in infinity as my upper bound and 1 as my lower bound. I didn't write that here because it's a little bit, takes more time than I need. But we're going to plug in infinity into this, and by that I mean taking the limit as x goes to infinity. And then when we plug in 1, we plug in 1. Limit as x goes to infinity. X to the 0.25 times 4 is just going to keep getting bigger and bigger and bigger and bigger. So when you plug in infinity, what happens is you get infinity. And then when you plug in 1, it turns out this is 4 times 1 to the 0.25, you just get 4. So you get infinity minus 4, which is simply infinity. And that means that this integration diverges. And so that diverges, therefore this infinite series also diverges. Okay? So it's that straightforward. Now, one thing you've hopefully caught is that both of these last couple of problems were 1 over n to a power. 1 over n to a power. And we've integrated 1 over x to a power from 1 to infinity previously this semester. And if you remember what happened there, when we integrated 1 over x to the p from 1 to infinity, that converged whenever p was bigger than 1, and that diverged whenever p was less than or equal to 1. Remember, when it was equal to 1, we integrate and we get natural log. So that 1 over x to the p is sort of has a cutoff value at p equals 1. Anytime p is bigger than 1, it's going to converge. Anytime p is less than 1, it's going to diverge. And so the same has to be true for this infinite series 1 over n to the p. Whenever p is bigger than 1, it's going to converge. Whenever p is less than 1, it is going to diverge. All right? And essentially what we're saying there, is that if you think about this infinite series, when p is bigger than 1, this underlying function goes to 0 quick enough to get a real number as our sum. And when p is less than or equal to 1, this goes to 0, but not fast enough for us to get a real number as our sum. All right? So that's the idea behind this. Now, this oftentimes is called the P-series test. So the P-series test, obviously, because we're talking about the exponent, the power of n here, but it's just comes straight from the integral test. So the integral test and P-series are essentially, P-series is just one version of the integral test. But again, it's very important that we get this. Anytime P is less than or equal to 1, this series diverges. Anytime P is greater than 1, this series converges. All right? That's going to come up over and over and over again. So I want you to take a look at these 4 infinite series and look at the underlying sequence that you're adding up. And based on that underlying sequence, determine whether or not the series converges or diverges. You don't have to go and integrate anything. You just have to realize when p is less than or equal to 1 versus when p is greater than 1. So go ahead and push pause on the video and try that out. So let's take a look at all 4 of these. I'm going to do this on actual Word document so that we can see it a little bit better of what I'm saying, but here we go. So infinite sum from 1 to infinity of 1 over n to the 8th. Well, simply put, p is equal to 8 this time. 8 is bigger than 1, so this thing is going to converge. So when I say this is going to converge, I mean the infinite series is going to converge because p is 8. All right, 8's bigger than 1. There we go. N here is raised to the power of 0.2. We're still doing an infinite series from 1 to infinity, 1 over n to the 0.2. That is going to diverge since p in this case is 0.2. All right. Again, p less than 1, we diverge. This one, the third one, n is raised to the 3/7 power. Now this looks a little uglier than what I had. N was to the 3/7 power. Now that is going to diverge because p is 3/7. Okay, 3/7 is less than 1. On our 4th infinite series, 1 over n to the 8/5, that has to converge since p is equal to 8/5, and 8/5 is obviously bigger than 1. All right. So we go that quickly. All right. Once you see these, this P-series test. P-series test allows you to do some assessing of these summations very quickly. Now, one other thing that I want to say before we log out of this thing, or we end this section, is that the convergence of the series using P-series test is not going to be affected whether or not I have a different number on top rather than 1, or whether I start my count at a number other than 1. This is pretty obvious in terms of the integral test, right? Because if I started at the top with a number other than 1, if I started with, for instance, like a 2 or a 5 or a 6 or whatever, I could have just factored that 5 out, and I would have had 5 times this and 5 times that. And infinity is not going to be affected by multiplying it by 5. Also, if a real number if this thing were to have integrated and given me a real number, then multiplying by 5 times a real number is still a real number. So it still would have converged if we converged. And the same thing is true with my start. If I started at a number like, I don't know, 4 or something, obviously that is not the issue. 4 here, the infinity is the issue. So starting my count at a number other than 1 is not going to be a big deal. So when you look at these two problems, take the infinite series 2 over n to the 8th, starting your count at 18 and going to infinity. Well, all we have to do is say, oh, that's just the p series. P is equal to 8. 8 is bigger than 1, and therefore this series converges. And similarly, 32 over n to the 0.2, starting our count at 3. All we have to do is say, oh, that's p series 0.2, as your p is less than 1, and therefore this infinite series is going to diverge. Let me write that down. There you go, I've wrote both down. So again, this infinite series, even though we started our count at 18, even though we had a 2 as our coefficient instead of a 1, that still converges because the n to the 8th power is the thing that that the integration is going to care about. So it converges, p is equal to 8, 8's bigger than 1, converges. Same thing, 32 over n to the 0.2, starting your count at 3. The important thing when we integrate is that p is equal to 0.2, which is less than 1. P less than 1 means diverging. Okay? So that's the idea of the P-series test. All right? So P-series test works. You don't always have to start at 1. You can start at whatever number you want. And obviously, it's pretty adaptable with coefficients. Now, in the next section, we're going to look at how this could have been compared to a P-series test. And this thing we did before can be compared to a P-series test using one of the comparison tests that, that we're going to look at in the next section. But we'll see that in the next section.